is Xiao Li, and I'm from the University of South Florida. It's my great pleasure to host this TFTC webinar in the ISTTT 21st series. And first, I want to thank all of you for participating in this webinar, despite the various time zones around the globe. I'd like to acknowledge Dr. Jack Haddard and his T-Smart Lab for supporting this conference system, and Dr. Jorge Lava from Georgia Tech to organize this webinar series. And also I'd like to thank my graduate student, Mosa and Pacified, for the technical help. So first of all, I would like to humbly ask all of you except the speaker to mute yourself if you don't want to talk. We just want to do this to minimize the background noise so everyone can hear the speaker clearly. So the way to do that is if you look at your control panel, left to it, there is a small ribbon with five or so icons on it, and one of them is a microphone. If you click it, it's going to toggle on or off the microphone. So that'll be a lot help. And we're going to have a presentation about 40 to 50 minutes, and then we have plenty of time to entertain with questions. So you can either speak out. At that time, you have to unmute yourself, or if you want to organize your words, you can use the chat box, which is the last. It's the last component on your GoToMeeting system. I'm going to talk about it later. So I'd like to let you know that the whole process is being recorded. Now I've already started to click this recording button. So, okay. So I'd like to introduce our honored speaker today, Dr. Ke Han. And Dr. Ke Han received his PhD degree in mathematics from the University of Science and Technology of China. He graduated from the Pennsylvania State University with a master's and a PhD degree in mathematics too. He joined the Department of Civil and Environmental Engineering at Imperial College London in 2013 as a lecturer equivalent to assistant professor in the US. He's also a visiting professor in the College of Civil Aviation at Nanjing University of Aeronautics and Astronautics. Dr. Han's research interests span a variety of aspects of transportation science and engineering, including traffic flow theory, network modeling and optimization, dynamic traffic assignment, traffic operation and control, network and mechanism design, sustainable transportation, urban logistics, and network resilience and robustness. To date, he has published over 50 journal and conference papers, co-authored 2 books, Dynamic Network User Equilibrium and Traffic Flow on Networks. Dr. Han is a member of the editorial board of Transportation Research Part B, a top journal in our field, and a guest editor for a special issue in Transportation Research Part C, which is also a very great journal. Part of his research is funded by the U.S. National Science Foundation and the European 7th Framework Program. He also undertakes consultancy work in the rail industry. And today his presentation topic is on data-driven decision rules for real-time traffic management. And yesterday, while we were testing out the system, we had a great conversation about his thoughts and philosophy about researching this topic and direction. I was very grateful for that, so I'm very looking forward to his talk today. So Dr. Han, welcome.
Okay. Hello, everyone. First of all, my thanks to Xiaopeng Li for hosting this webinar, and of course for Traffic Flow Theory and Characteristic Committee from TRP for hosting this webinar. So my talk today is titled Data-Driven Decision Rule Approach for Real-Time Traffic Management. So this is a paper presented at ISTTT last year. And the title of that paper is actually going to be Linear Decision Rule Approach for distributional robust optimization for traffic signal control, which is essentially part 1 and 2 in this talk. In the third part, I'm actually going to provide a few extensions as well as applications that has been going on since the presentation of the paper. So we have some interesting research based on this paper. So I will discuss that as well at the end of the presentation. To start with, I'm first going to introduce the notion of linear decision rule. And so on the first slide, I'm actually going to discuss decision rule in general. Of course, the application here is traffic signal, but it doesn't have to be like that. I think this is a more general approach for dealing with traffic in real time in general. So real-time traffic signal controls has met several challenges. To start with, the need for us to generate fast decisions, oftentimes within a matter of seconds. And often we have to deal with nonlinear, non-convex, and even non-analytical objectives, including safety index, emissions, so on and so forth. And because of the limited time resources, oftentimes we have to resort to distributed or decentralized controls rather than system-wide optimal. And last but not least, we're often dealing with uncertainties that could arise in within-day or day-to-day traffic variations. So in dealing with all these issues, there has been quite a lot of heuristic methods proposed. However, they are often inexact and are sometimes rendered suboptimal because of the several reasons mentioned above. So in this presentation, I'm going to introduce this new paradigm called decision rule approach for real-time traffic management. And here are some of its key features. It utilizes historical and real-time data with within-day or day-to-day variations. And here we're relying on what's called distributionally robust optimization, which is a relatively new technique for handling uncertainties. And the decision rule is fairly efficient for real-time operational environment. The computations involved is minimum. And this approach is also compatible with analytical or simulation-based approaches. So just to illustrate the basic idea, on the right-hand side, we have a diagram showing some of the very fundamental elements, starting with real-time system state collected by real data. And what the decision rule does is it proposes a certain functional form that transforms the system state into whatever control parameters that we're dealing with. And this transformation is often analytical or closed form. And if that's linear, that's what we call linear decision rule. Or if it's nonlinear, then it's nonlinear decision rule.
How much did you buy the green?
What?
Yeah.
The greens.
Brain. My brain?
Yeah.
How much?
Yes.
Sorry,
We
can
have some background noise.
yeah, yes. Let me see. Can the audience mute yourself if you notice that I hear quite some background noise?
Okay, I
Okay,
think we're good. Yeah.
I think it's good.
Yeah. Of course, such analytical transformation is almost arbitrary. So we're going to have a feedback loop that can somehow provide feedbacks and inform the best way to choose such an analytical transformation. And this often involves computation of key performance indicators through simulations. So that's the basic idea of this decision rule approach. And now, in the context of traffic signal control and specifically linear decision rule, here's an example of how this works. So we're going to start with Q here, which represent real-time information, and in this context, it can be quite arbitrary: flow, count, speed, Q, etc. And in case of linear decision rule, here we're imposing linear coefficients A and B. So A, B can be both matrices. AQ plus B gives us the linear transformation. But of course, sometimes when we're dealing with controls, we have lots of constraints, and therefore sometimes we have to project whatever quantity here onto the set of feasible controls to come up with a feasible control U here. So here on the right-hand side, we have a diagram showing the transformation from Q all the way to U here. But that's not the end. In the end, we're going to have a network performance measure denoted as psi here, and it depends on the real-time information Q and the control U here. So we're going to have a network performance measure here usually conducted through simulation to actually to say whether or not such control here U is optimal given such information Q. So in summary, the problem here can be stated as follows. Given real-time information Q, we're going to find the best linear decision rule, which means finding the best A and B, such that we're going to minimize this performance measure. And of course, here we assume that psi is subject to minimization without loss of generality. Of course, this is a deterministic problem in the sense that the real-time information Q here is known, but oftentimes we're going to have stochastic inputs, and I'm going to discuss that later. But before that, let me just illustrate a bit more about the details of the linear decision rule and how that exactly works. Here we have this matrix is what I call observation matrix. So that's where the real-time information is contained. Here we have Qs, and the superscripts 1, 2, and 3 indicate time steps. The lower scripts A, B, and C, they can refer to different locations where the data is collected, or they can refer to the different data type. So anyway, these are quite general indices. And given such matrix, we can actually apply a certain transformation, say A1 times Q plus B1, and that gives rise to control U1 at certain location, and we do the same for all the other controls. So in the end, with a little bit of abuse of notation, let me just write U equals A Q plus B. Here U is the control here. And of course, the dimensions of A and B is almost arbitrary. One can choose them according to the situations. For example, we can say that given the current time t, whatever decision we're making right now depends on the past t observations, for example, because there are certain delays in the system. So you can arrange the dimensions of A and B accordingly to accommodate this need. So that's how the decision rule works in general. Now let me just say a few more things about the decision rule here. In the context of traffic signal control, oftentimes we have constraints on the signal control parameters such as maximum and minimum green time, offsets, and so on. So we're going to have to find ways to actually project whatever AQ plus B onto the set of feasible controls, omega here. And here's a relevant proposition. If we can somehow express all these constraints using linear forms, then we can show that the projection looking like that is actually equivalent to a set of linear constraints with additional binary variables. And the reason that's relevant is that later on when we present a mixed integer linear program formulation, we're going to need to maintain linearity here. So at the end of this first part, let me just introduce the stochastic extension, and that's the real problem we're dealing with here. In reality, whatever observation vector Q here is stochastic, subject to within-day or day-to-day variations. And one of the ways to do that, the conventional way, is to invoke stochastic programming, which of course rely on exactly known knowledge about the probability distribution. And this, unfortunately, is not true in reality because we can only collect finite number of samples. And therefore, whatever distribution will come out of it is ambiguous. So based on, given the situation, we propose a distributionally robust optimization. For those of you who are unfamiliar with this term, it is very much similar to robust optimization with the exception that we're dealing with uncertain distributions instead of uncertain parameters. So DRO is a generalization of RO. Now let me just state the distributionally robust formulation here. Given stochastic input Q, we're going to find, again, the best linear coefficients A and B, such that we're trying to minimize this quantity here. And here max means that we're looking for the worst case scenario, which is quite often seen in robust optimization. And among all candidate distributions, here what's uncertain is the distribution here. And actually this approach subsumes the stochastic optimization, because stochastic optimization, we have a known distribution. In other words, the uncertainty set contains just one element, which is the known distribution. So stochastic optimization is just a special case of our approach. And also because of the practical situation where we can only collect finite number of samples, And oftentimes, such samples are far from being sufficient when it comes to a very complex, high-dimensional system. So we're going to invoke a data-driven calibration approach for the uncertainty set Q here. So we're dealing with a minimax problem, and we're trying to look for the worst-case expectation of the performance measure given stochastic input. Here are some advantages of the linear decision rule approach. When we combine that with distributional robust optimization, we're effectively reducing the problem of real-time control into finding the best A and B here, and that's very precisely stated as such. It allows a very viable and efficient online operation because all of the expensive optimizations are moved to an offline environment. And during online operation, all we have to do is to simply perform linear transformation and possibly projection, which are both very tractable and very easily implemented. It allows a very flexible sensor location, data type, and control resolution, as we have seen before. And it also allows a user-defined feasible set for signal control parameters, which is omega here. And in this presentation, we're going to introduce two methods for solving this problem, one based on mixed integer program, and the other one based on meta-heuristic search. So now, in the next part, let me just introduce how we're going to solve this highly complex DRO problem over here. And before that, let me just introduce the data-driven calibration of the uncertainty set. And this happens to be a very key issue here because in conventional robust optimization approaches, sometimes we often just use a very simplistic box constraints or polyhedral constraints without considering actually the distribution of these data points. And that oftentimes leads to very conservative controls, which has been criticized. So here, we're trying to come up with a data-driven calibration approach based on the KS test. The KS goodness of fit test basically it tells whether or not a given distribution captures well a given set of samples up to a certain confidence level. And it boils down to the following hypothesis test. Suppose that we're given several data sets indicated by Q here, and they're historical data. Here, we assume that each element of the data follows a marginal distribution here. Here, star means it's the true distribution, which of course is unknown to us. So the KS test simply says whether or not a given distribution can be seen as the true distribution up to a certain confidence level. And the null hypothesis can if the following inequality holds. So based on the KS test, we can easily construct the uncertainty set to be the set of all distributions for which the null hypothesis will not be rejected by the KS test. And that can be, again, expressed by inequality constraints. So this is going to be the uncertainty set. And we can say that with confidence alpha, we can say that this set contains whatever true distribution there is. And before I move on to the solution method, I think it's necessary to introduce a few reductions of the notation because so far we're dealing with a very complex, messy expression. So from now on, I'm going to replace the decision variables A and B with X, and the network performance measure as F, which depends on the decision parameters and also depends on the inputs. So this is nothing more than just a change of notation. So we're dealing with this problem over here. Now, to introduce the mixed integer linear program, we started off with the following full problem. This we have just seen. And the expectation can be expressed as the integration over the uncertain domain of the quantity times its PDF. So, and the PDF is bounded from up and below by these two quantities, which are essentially given by the KS test. If you go back here, so these are the upper and lower bounds. And here we're using simplified notations, of course. But this problem is barely solvable because for starters, it's a min-max problem, which means it's bilevel, it's non-convex. And second of all, it's infinite dimensional because we have infinite integration here. So we have to deal with these two problems. In dealing with the first problem, we actually invoke dualization, and by invoking weak duality, we can actually reduce the bilevel problem into a single level problem here. It's not entirely equivalent to this problem because it's only weak duality, but we can show that the solution of this problem is an upper bound of this previous problem. So by minimizing the upper bound, we can simultaneously minimize this problem. But again, this is not enough because this is still finite dimensional. So we have to introduce a discretization of the uncertain space. And for that, we invoke the finite sampling approach and reduce the problem into this form. I'm not going to introduce the details about these approaches, and you can find the details in the paper. And we actually have theoretical results guaranteeing the performance of these approximations. So looking at this final formulation here, we have everything almost in linear form and finite form, of course, except this term over here. If you recall, f over here, that's the network performance function. X is the control, and p here is the input. So provided that this one over here can again be expressed as a linear form, we are guaranteed a mixed integer linear program. Fortunately, there has been lots of papers that discusses how we're going to discretize the kinematic wave model, and with the help of integers, we can express kinematic wave models into linear forms. And several papers, including Xerostopoulos and the link transmission model by Yepperman, we can easily actually transform kinematic wave dynamics into linear constraints with binary variables. So I'm not going to state the entire problem. Again, you can find the detailed formulation in our paper. So far, we have introduced the mixed integer linear program approach, but of course, that has some limitations. For starters, we have to have linear signal constraints because if you recall early on, in order to maintain linearity, we have to assume that this set omega has to be expressed using linear terms. And while that's okay for signal control problems, but there may be times where the set of feasible control is not linear. So we may have to get rid of that. And the more severe problem is that in the process, we actually assume that the individual components of these stochastic input, they have to be independent. And this is a very restrictive assumption. And the reason we need that is because we need to apply the KS test to these quantities. And we cannot do this if we treat them as a multivariate problem, because KS test can only apply to one-dimensional problems. So what we actually did is by assuming independence, we can break down the distribution function into individual ones, and we can apply the KS test to individual ones, then simply just multiply them all together to get the joint distribution. So that's why the independence assumption is invoked here. And finally, in general, for MIOP problems, it's computationally intractable. It scales badly when the problem gets bigger. So here, as a second approach, we're proposing heuristic methods, and it has the following advantages. We can define very arbitrary feasible signal control set and objectives, and it is free of the independence assumptions. So we can treat this multivariate stochastic quantity arbitrarily, regardless of the independence or correlations between its individual components. We can apply the heuristic method to solve potentially very large-scale problems with more realistic settings. And also, the heuristic method, there are lots of methods that rely solely on zeroth order information of the objective, which means that all we have to do is to keep trying different solutions, computing its objective values. And based on those information, we keep on searching until we find a better one. It does not involve any gradients or hashing, any other information about the objective or the constraints. The heuristic method is also compatible with analytical and simulation-based traffic models, and later on I have a slide showing that, how we did that in microsimulation environment. For this particular paper, we're using particle swarm optimization, but of course, I don't see any reason we cannot use other heuristic methods as long as it's based on zeroth order information. Now, to actually use heuristic methods, we have to deal with this KS test because now we're dropping the independence assumption. So how does this work? Actually, it's quite simple. Here, we know that Q is multidimensional, it's complex. So we're not going to deal with Q, we're not going to apply KS test to Q here. Instead, we're going to apply the KS test to the objective function because we know that it's just a scalar. And also this function f, the quantity itself, is going to be random because of the randomness in Q. And also this one is parameterized by x. So given any control x, and because the Q is stochastic, the f is also stochastic. So all we have to do is to understand the stochasticity of Q, of f over here. And therefore, for a given x, we also have uncertainty set for the f here, which is again parameterized by x. So the problem we've been dealing with over here can be rewritten as such. For this problem, the uncertainty parameter is Q here, and these are all about Q. But for this problem, everything is about f over here. So how do we apply the KS test? Well, we're going to assume that we have several samples, let's say K samples of these inputs. And we're going to, for each sample, we're going to perform simulation and compute the objective value f here for a given x. Here x is given. And now we have a bunch of samples for f. So we can apply the KS test for the f and come up with something similar. We have seen this before. So the next thing to do is we want to make use of this information, of this uncertainty set. And now we want to find the worst case expectation given this uncertainty set. So the way to do that is as follows. Here we have random variables f parameterized by x. And what we did is we come up with the lower upper bounds of f. Here, lower and upper bounds. And then we're going to partition this interval into several equal subintervals. So effectively, we're coming up with a discretization of the PDF. Now, in constructing the distribution function, all we have to do is to determine the heights of these rectangles. And those are denoted by these values. We know that each one of these values has to be bounded from up and below because of the KS test, which essentially comes from here. So for each one, we have an upper lower bound. And also we know it's a PDF, so the integration of that has to be 1. The sum of squares, the sum of the area of these rectangles has to be summed out to be 1. Given these constraints, plus non-negativity, of course, then we can compute the expectation in this form. So now, because we want to find the worst case, all we have to do is to maximize this expectation subject to these, this, and that constraint. And that's how we come up with the worst case expectation. And this problem is actually going to be a linear program, which is very easy to solve. So in this slide, what we have just discussed is actually going to be a way to evaluate the objective value for the entire problem, for the original problem. So let me just summarize the procedure here. Here, we're trying to compute for each given control the objective value of this problem. And once we can do that, then we can apply any heuristic search method to find the optimal x. So the way to evaluate the objective function for a given x is as follows. Given x and historical data, k of them, we're going to conduct traffic simulation to compute the objective value for each one of these q's. And then we're going to calculate lower and upper bounds, which is given here and also here. So these two expressions. In the end, in order to evaluate this maximum, all we have to do is solve the linear program, which is here. So that's how we compute the objective value. Now, when we know how to do that, then all we have to do is to apply particle swarm optimization and compute, keep improving X till we find the best solution. So just to show how this works in an actual numerical example, here we have obtained a network from west end of Glasgow, and with 5 signalized intersections and several 35 directed links. For the traffic flow model, I'm using LWR traffic flow model. And as far as data is concerned, we have obtained some data about the turn-by-turn flow count at each intersection for the period of 1 hour in morning rush period. And we obtain daily variations synthetically because, unfortunately, the data we get here is only for 1 day. So we have to manually generate synthetic data variations according to certain pseudo-random numbers. But the important thing to address here is, although we generate the data with known distribution, our method assumes no such information whatsoever. In other words, whether it's a real data or it's synthetic data, the proposed approach does not assume any information on the distribution. And as a comparisons, we have fixed signal timing solved either using deterministic flows, so in other words, we base that on the averaged flow, or we apply distribution robust optimization to fixed signal timing. And also we compare that with the field signals parameters provided by the Glasgow City Council. That's the signal timing they're using for certain periods of time. So let's just see how things work. To start with, I'm going to test the KS test. So here I'm showing you a illustration of the construction of the uncertainty set. On the left-hand side, we have several samples of flow variations, one color for 1 day. And as you can see, the variation of flow is quite substantial. Here, the black curve here, that's simply the average of these ones. Here I'm just showing 5 of them, but there are actually 30 of them. On the right-hand side, based on all these 30 samples, here's the uncertainty set for the CDF, the cumulative distribution function. The gray dots, that's the real distribution, that's the true distribution. And these colored ones are the uncertainty set with different levels of alpha. So if alpha is small, that means the confidence level is high. Actually, the uncertainty set is the biggest. And that's very understandable. And when the confidence level gets lower, the uncertainty set becomes smaller and smaller. And actually, they all capture very well the true distribution. So let me first test the mixed integer linear program. And we solved this problem for 2 time horizons, 400 seconds and 800 seconds. And we compare our proposed approach with the deterministic fixed timing. So the way we come up with these solutions is we take the 30 samples and we simply compute the average of them, just like this. And then we apply the average flow to a deterministic optimization problem, simply solving another mixed integer program and coming up with a fixed signal timing. So as you can see that in terms of objective throughput, our method outperforms the benchmark significantly. Here, the objective is calculated, is expressed as such. It's a linear objective, and we'll maximize the sum over all time. LR denotes all the outgoing links in the network on the boundary, and delta T is the time step. So by doing that, we actually, not only do we maximize throughput, but also we encourage early arrivals as much as we can. So in this way, this objective tends to maximize throughput, but at the same time, minimize delay. Now going to the heuristic search methods, we compute the problem for a period of 1 hour using particle swarm optimization. Basically, the offline computation takes much time, which is 24 hours, but that's not a big deal because it's offline. Whereas the online implementation is almost negligible. Basically, for our approach, it takes 24 hours for the offline computation, but only less than 1% of a second to finish online computation. Now, for comparison, we have this deterministic fixed timing like before, and also we have this distributional robust optimization with fixed timing. So here we're taking into consideration the stochasticity of things, but stipulating that the control is fixed timing. It's not responsive. And also over here we have field data from the test site. As you can see, our approach outperforms all of them, and especially when you compare this one with DRO but with fixed timing, the improvement is quite substantial, which highlights the need for real-time control. And here, if we assume that everything is deterministic, actually the performance is very, very bad, because partially from this picture you can see that ignoring the variations of flows, that can be quite bad. So that's why this number is far below the other ones. Now let me just show you how we can similarly do this for microsimulation environment. Here, for all these computations, what I did is using LWR model, which is a deterministic traffic flow model. But we know that there's a lot more stochasticity, especially in the network performance model. For example, in a microsimulation environment, the uncertainty is far more than just boundary flows. It can be somewhere within fleet composition, vehicle dynamics, and even route choices. And all of that can be, again, encapsulated within this uncertain parameter Q here. Here, X can target very complex parameters such as cycle time, green time, offset, etc. And F, again, can include vehicle-specific or system-wide objectives. So given the control X, the objective is a very random variable. The stochasticity is almost intractable because there's so many sources of uncertainty. But again, ignoring all that, just focus on F. We can again invoke the KS test to F and come up with the exact same approach as we've discussed before. So here's an illustration of the results. We have this test network 4x4 with 8 zones and 28 OD pairs, and the route assignment is dynamically given according to some shortest path, real-time shortest path algorithm. The fleet composition includes passenger cars, LGV, MGV, and HGV, and as well as buses. We're using 4-stage signal plan at all 4 junctions, and to generate stochasticity, we're using 30 random seeds for generating the samples for training the model, and we use another 30 random seeds for testing. So here on this picture, we're showing our approach versus the base model, which is the equisaturation policy implemented at each one of these single junctions. So as you can see that our approach outperforms the base model, and also even in the worst case, which is probably here and here, our model is again works quite well thanks to the robust optimization approach. On this picture over here, I'm showing you the computation for another scenario, I believe with higher degrees of saturation because the delay is higher. But the point of that is we have computed after we have trained the model, we apply that to 30 test data, and this is the summary about its objective, which is the average delay. This green bar over here, that's the worst case objective value computed from the distributional robust optimization. So the point here is that indeed this line captures the majority of these samples in the sense that it's the worst case scenario. It does ignore 2 outliers over here because this is, after all, a probabilistic model. It does not capture all of the stochasticities. As a matter of fact, if we were using robust optimization, we're going to have to include these 2 points as well, and unfortunately that would make the problem way too conservative. And that's why we're coming up with this probabilistic guarantee, which strikes a balance between conservatism and tractability. So as a summary about what we're dealing with here, we started off with a linear decision rule, and by fusing network information into this, we come up with a deterministic problem, and because of the daily variations, we have a stochastic problem. And because of the uncertainties in the distribution, we come up with a distributionally robust optimization to make sure that the performance of the model is optimized, even in a very, very adversarial situation. And then we invoke the KS test to handle the potential problem of insufficient data and ambiguity in the distribution estimation, and coming up with two explicit reformulation. So this paper is published in Transportation Research Part C and also presented at ISTTT in Kobe. So for the last part, I'm going to present very quickly several extensions and applications of what we have discussed. As its title suggests, this presentation is more than just signal controls. It can deal with a wide range of applications in traffic management. Let me first start it off by having discussion about nonlinear decision rule. Linear decision rules can be sometimes quite rigid if the dynamic is sufficiently nonlinear. So to deal with that problem, we actually involve artificial neural networks. So the problem is almost the same over here, except that the so-called function here is actually quite implicit. And in our particular example, we're using two hidden layers with several neurons and several fixed form for the activation functions. And the quantities to be determined are going to be the weights of these individual connections. So this is very much like the linear decision rule, except that the functional form is nonlinear. And a comparison of their performance for the same classical network shows that the nonlinear approach performs slightly better than a linear decision rule approach, which is expected. And the second extension involves multi-objective. The decision rule approach we have discussed actually allows for very sufficiently nonlinear or non-analytical objective functions, which can include emissions. So here I'm looking at a problem with both throughput and emission as the objective. So we're dealing with a multi-objective function. For emission models, we consider hydrocarbon, and based on the kinematic wave model, we derive speed, density, and acceleration, deceleration for the input of the instantaneous HC emission model. Here I'm showing you what appears to be pretty much a frontier with different values of W, although we shouldn't really call that frontier given that the heuristic method does not always give us the best solution. But you can still understand the trade-off between throughput and total emission. So here, when W equal to 1, effectively we're ignoring the emissions. And you can see there's a huge margin for reducing emissions at a cost of throughput. The next application involves, okay, this is the first application, so now we're done with signal controls. But here we're looking at an application in variable message signs, which in principle is very much like signal control. Here we're dealing with a real network here in China, and we have in afternoon rush hours, we have a VMS over here. And the VMS actually displays 5 different status. So this means go left or right, and 2 arrows means it's a strong suggestion. And this one means there's nothing displayed or no suggestion. And each display comes with a different compliance rate. And we collect data for several days on the site. For this period, 4 to 5 in the afternoon involves more than 10,000 vehicles. And we're mainly dealing with 2 alternative routes over here. For the model, we use dynamic agent-based simulation, and we use 10 days of data for training and another 10 days for the testing. So here summarizes the average delay when different strategies are used, no VMS, and with VMS. So true information, that means we're displaying everything honestly, with no other hidden information. It's quite interesting actually to see that displaying true information is not the optimal way to do things, actually. If we invoke the linear decision rule, actually, we can save even more travel time, actually, on average 5 seconds per vehicle, and that's quite significant compared to this true information, and that's quite interesting. So the final application I'm going to discuss involves a whole different area, which is air traffic management. So this is actually part of a bigger project that my PhD student and I were working on. But let me just give you a very quick background story. Here we're dealing with the design of terminal area for uh, Maltese airport systems. Here we're looking at the New York airport systems with empirical arrival and departure aircrafts. And as you can see from this picture, it's not very efficient. Involves lots of delays and diversions. So what we did in this project is we come up with a new way of designing airspace routes based on the principle of shortest path, flyability. It's based on priority and conflict-free. And this approach has actually been validated during our visit to the Port Authority of New York and New Jersey. But that's just background story. The key application of our approach has to do with the real-time terminal airspace design, because these routes I have shown you before, these are only tactical routes or pre-tactical routes. In the real time, we have to adjust these routes according to real-time traffic demand. So we're going to invoke a rolling horizon basis. So the way this works is we receive demand forecast for both departure and arrival every 1 or 2 hours beforehand. And of course, that demand forecast is uncertain. There's error associated. And in terms of demand, it has several attributes, including aircraft type of operation, origin destination airports, passenger or cargo aircrafts, and domestic or international, and direction. So with so many different attributes involved and some uncertainty, some parameters are discrete, some of them are continuous, it's impossible to actually manage in any way to manage the uncertainties directly. But fortunately, with our approach, we can just focus again on the performance measure, F over here. So here I'm presenting a general formulation for this problem, where again we have to optimize the linear or nonlinear coefficients given the deterministic demand prediction plus stochastic prediction error. So the way we do things is whenever we receive P, the prediction, we apply a transformation through X, and then add on the stochastic prediction error to come up with the calculation of F. And from there, we can characterize the stochasticity of F, and everything follows as usual. So with that, I think that's all for the main content. Here, as a very short summary, we're introducing this decision rule approach for real-time traffic management. It's very effective. It's actually a special case of the feedback control in the sense that we're stipulating its functional form, whether it's a linear, nonlinear, or other forms. It allows a very flexible objective and constraints, and it allows a very feasible real-time operation because all of the expensive computations are moved to an offline environment. It relies on the probabilistic guarantee via the offline optimization through robust optimization, and it is widely applicable not just to signals but a range of applications in traffic engineering. Regarding the DRO, it relies on uncertain distribution. So this is especially very useful when there is a lack of data. When you have an insufficient sample size, the estimation of distribution function is quite unreliable. So that's why we have to rely on this robust approach. It strikes a balance between the tractability and conservatism. Tractability is often not seen in stochastic programming, whereas a robust optimization is often criticized for conservatism. And our proposed DRO approach actually finds a balance. And it works well with the combination with decision rules. So in the end, let me just quickly say thank you to some of my colleagues, some of them are my PhDs, for contributing to the presentation, especially the third part. We have actually quite a lot of active research going on, which are inspired by this decision rule approach. And I hope that you find it interesting and enjoyable as well. So thank you very much for your attention. I think we can move on to the question session.
Thank you, Dr. Han. Quite a nice presentation, combining
Thank
the
you.
elegance and rigor of the exact solution algorithms and the flexibility of the heuristics. and also very general methodology, many applications. So I enjoyed the presentation. I guess everybody else does, as evidenced as a very high attendance. So uh, at this time, I guess we're open for
Mhm.
any questions and comments. So you can unmute yourself and also ask Mohsin to unmute the audience from other side if you think so. You can speak out or to raise your question, or the other option is to use the chat box, which is the last drop-down panel on your GoToMeeting console. And if you want to use chat, please make sure that you send the chat to organizers and panelists only, which is the third option, which is the third, well, I don't know which option, but anyway, you, you need to send a chat to organizers and panelists only, okay, in that Dropbox here. So we've already received one
Yes,
question.
I saw that.
Uh,
In KS test, shall I answer that?
yes, of course.
Okay. So the question was, in KS test, do you assume that volumes in consecutive time intervals are independent? And the short answer is, well, for the mixed integer program approach, yes. As you can see here, we're breaking down the input into, in this case, I denotes the link, and T denotes the time. And here we're breaking it down into these individual components, and we assume that each one follows the marginal distribution. And we assume that they are independent of each other. That's the assumption we make, because we cannot apply KS test to multivariate quantity variables. And we have to assume independence to deal with them individually.
We received the second question from Dr. Chiesenjo.
Yes. Dr. Han, do you develop and embed your own traffic simulator or use external simulators to evaluate different performance functions? In this case, both. For the paper, for the IEEE paper, I'm using LWR model, which myself, the algorithm I developed myself. But later on in these applications, we actually use S-parametrics. As you can see here, over here, we use S-parametrics, external simulation functions. And also in here, in this VMS, we're using agent-based simulations, and one student actually programmed that by himself. So I think this approach actually allows for both external commercial solvers and as well as the ones that we develop ourselves. And later on, we're actually planning to combine a emission model with parametrics. The emission model is called AIR, to come up with a more realistic representation of emission. So all of these can be done within our framework. Yeah. Have you compared your signal control results to those from alternative signal optimization methods such as adaptive control? That's a very good question. As far as the paper goes, we haven't done that because that will involve much more work. We have ongoing research where we compare. We're trying to implement this whole framework into VISM, and we're going to use the Scoot module from VISM and come up with a more fair and comprehensive comparison. So we're actually doing that right now. In the paper, we only considered these different alternatives. The one that's relevant to reality is the field parameter provided by the City Council. Thank you.
So okay, Dr. Han, while others are still preparing their questions, or I'd like to ask you about you showed heuristic and to solve that worst case, and I remember there is one page about the yeah, this page right here. So when I look at it, you use linear programming, right? I'm wondering, based on this structure, is there a simple the solution is simply solved by ranking. I don't know if I'm right or not, but I don't know if you have other constraints, but just if you have
I'm sorry, I think we have some background noise. Go on.
okay, all right, okay, I'm sorry about. So, but you have a box constraint, non-activity constraint, and summations with one, right? So
Yeah.
I'm just wondering whether like really assignment would work. So just assign a maximum weight to the worst fi, and then if that reaches a boundary, and then you can
Uh,
assign the second worst. So this way, I think you basically want to maximize this the weighted summation of
yeah.
fi.
Yeah. Yeah. Yes. That's right. But I think what you described is essentially the way to solve this linear program. Because what this tends to do is it tends to within the constraint of the KS test, it tends to shift everything to the right, make it right skewed. That's where the worst case lies.
Okay,
Hello?
yeah, I would
Mm.
also
Yeah.
ask
So yeah.
some of you mute the background if
So,
you may. Mhm.
so as a result of this approach, what it does is it tends to shift everything as much as possible to the right-hand side,
Right.
because
So
that's how you maximize the expectation. Yeah. But of course, there are uh, for us the easy way is to solve this linear program. Yeah. Of
right,
course. I think your description is another way of coming up with the solution, but I think it's just will be the same as the linear program.
right. I mean, the solution will be the same. Maybe it can be more. I mean, you can see the solution structure, and you don't have to run a linear program solver. The ranking works. I don't know actually. I
That's right.
just assume.
That's right. For the understanding of this approach, how this worst case comes up, of course, it will be good to actually have a visualization of things, coming up with several examples. But as far as computation goes, I think the linear program is easy enough to solve.
Right.
And so, yeah, so
Okay,
we
great.
just did that.
So and and also so looks like this meta heuristic approach work for like closed loop problem where Q depends on X? It should also work, right?
Yes. Essentially, we are dealing with a closed loop problem. It's just that it's a constrained closed loop problem because we're stipulating. It's like you have a closed loop control, but you have a stipulation that the control takes the form of linear control. And then the problem becomes to find the optimal control strategy. All I have to do is to find the linear coefficients. So I think essentially this is dealing with the closed loop control problems because
Okay.
it's a responsive control problem. Yeah.
All right. Great. Thank you. Let me see.
Okay.
Is there any other questions? I'm looking. Uh, is there any other questions? Okay. Well, by then I want to thank Dr. Han again for his nice presentation and very in-depth illustration explanation of his past and recent work. So I learned a lot myself. I much enjoyed the presentation. And I also want to thank all of you for dialing in this webinar. And our next week we won't have a webinar, but the next webinar will be 2 weeks from now, and you're all welcome to dial in again. And with this, I would like to thank you all very much. Hope you have a great weekend. The webinar adjourns.
Thank you very much.
Thank